You have watched a rocket launch before. Maybe on your phone, maybe on a giant screen somewhere. And every single time, without exception, your eyes go straight to that massive machine sitting on the launch pad. The fire, the roar. That feeling in your chest that no screen can fully contain. But there is one detail your brain has absorbed on every single launch. Something completely visible, completely obvious. Something you have looked at hundreds of times and never once stopped to question. The color every rocket you have ever seen is white. The Saturn V, the machine that carried human beings to the moon, white. The Space Shuttle, white. SpaceX Falcon 9, white. NASA's Space Launch System, white. China, Russia, India, Japan, Europe, white. Every time, without exception, across 70 years of space exploration, across every country, every program, every era, they all arrived at the same color. Now here is the question that has been sitting in plain sight this entire time. Was it tradition? Was it aesthetics? Did one engineer choose it in 1958 and everyone simply followed? Or is the reason buried so deep in the laws of physics, so precisely calculated, so critical to the survival of the vehicle, that choosing any other color could cause the rocket to destroy itself before it ever leaves the ground? That is what this video is going to answer. To understand why color matters on a rocket, you first need to understand what a rocket actually is. Not the engineering definition, not the textbook version, what it actually is. A rocket is, at its core, a sealed metal container filled with the most volatile substances human beings have ever learned to control. Liquid oxygen cooled to -183 degrees Celsius. Liquid hydrogen cooled to -253 degrees Celsius. That second number deserves a moment. -253 degrees Celsius is just 20 degrees above absolute zero, the coldest temperature physically possible anywhere in the universe. This fuel is not merely cold in the way a refrigerator is cold. It exists at a temperature that barely exists in nature outside of deep space. And it sits in thin aluminum tanks on a launch pad in Florida. In direct sunlight, the Saturn V rocket carried 2,000 tons of this propellant. The explosive energy contained in a fully fueled Saturn V is roughly equivalent to a small nuclear weapon. Not metaphorically, physically, by actual energy calculation. That is what is sitting on the pad, waiting, while engineers run their checklists. Now the sun over Kennedy Space Center delivers around 1,000 watts of energy per square meter of surface on a clear afternoon. That energy does not pass through metal. It is absorbed by it, and as it is absorbed, it moves inward, slowly, steadily, through the aluminum skin of the rocket, toward the tanks, toward the fuel. Inside the tanks, the temperature of the propellant begins to rise degree by imperceptible degree. As it warms, the liquid begins to expand. The pressure inside the tank climbs. These tanks are engineered for precise pressure ranges. They are not designed to flex. They are not designed to absorb surprises. If the pressure builds past a critical threshold, the tank does not slowly leak. It fails completely, on a vehicle carrying the energy of a nuclear detonation. So when the engineers of the 1950s and 1960s sat down and asked what color to paint this machine, they were not making an aesthetic decision. They were making a structural one. And the answer they calculated after thousands of thermal tests and engineering reviews was the same answer that has been used on every rocket ever since: white. Here is what white paint actually does to a rocket, and why the choice is more precise than it appears. Sunlight arrives at Earth carrying energy across a full spectrum. Some of that energy is visible light, the colors the human eye can detect. A larger portion is infrared radiation heat energy that is invisible but physically real. When sunlight falls on a dark surface, that surface absorbs roughly 90 to 95% of all incoming energy. both the visible spectrum and the infrared, the surface heats up quickly, deeply. The energy moves through the material. When sunlight falls on a white surface, 80 to 90% of that same energy is reflected away before it can be absorbed. The numbers seem similar. The difference in practice is enormous. A dark-painted rocket sitting on the launch pad on a clear Florida afternoon can reach surface temperatures of 70 degrees Celsius, hot enough to cause burns on contact simply from sitting in the sun. A white-painted rocket under identical conditions stays close to ambient temperature. Now follow that difference inward. The liquid oxygen inside the tanks must remain at minus 183 degrees Celsius. The liquid hydrogen must stay at minus 253. Every degree of unintended heat that migrates through the rocket's skin means the cryogenic systems work harder to compensate. It means more fuel is consumed just managing temperature before the engines ever ignite. It means the margins, those precisely calculated safety ranges that engineers spend years refining, begin to narrow. Narrow margins in rocketry are not a minor concern. They are the difference between a nominal launch and an investigation. By painting the exterior white, engineers reduce solar heat absorption by up to 90% compared to bare or dark-painted metal. That single layer of paint keeps the vehicle within its thermal envelope for hours, sometimes days before launch. It is, in a very literal sense, the first line of defense between a controlled mission and a failure on the pad. But white paint is only part of the answer. Because as engineers studied the thermal behavior of rockets more deeply, they discovered something that complicated everything. Different parts of the rocket had completely opposite thermal needs. And solving one problem created another. Look closely at a photograph of the Space Shuttle on the launch pad. The orbiter, the winged vehicle that carried the crew, is white across its top and sides. But the belly is jet black, not partially black. Not black in certain areas. Every square centimeter of the underside covered in thousands of small black tiles. This was not a design choice made for aesthetics. It was the product of a thermal problem that white paint simply could not solve. Here is the physics that engineers had to confront. White surfaces are exceptional at one thing, reflecting incoming radiation away before it can be absorbed. But white surfaces are poor at the opposite task, radiating heat outward. Dark surfaces, by contrast, do both. They absorb heat readily, and they release it readily. A dark surface sheds thermal energy into the surrounding environment far more efficiently than a white one. During re-entry, the Space Shuttle's belly faced plasma at temperature approaching 1,650 degrees Celsius, hotter than flowing lava, hotter than the surface of many stars. Those 24 zeros and black tiles were not simply protecting the aluminum structure beneath them from heat. They were actively managing it, absorbing it at the surface, containing it within the tile material and radiating it outward so that it never transferred to the vehicle's skin. Reroam those tiles and replace them with white. The shuttle does not survive the descent, so engineers were left managing a vehicle with two completely opposite thermal requirements. White on the areas exposed to solar radiation before launch to reflect heat away. Black on the areas facing plasma during re-entry to absorb and radiate heat outward. Same vehicle, same flight. Two fundamentally different thermal environments, addressed with two fundamentally different colors. The rocket was not painted one color. It was mapped surface by surface, according to the thermal demands of each individual section. And then, just when this system appeared to have reached its final form, one engineer looked at the weight numbers and proposed something that seemed, at the time, like an elegant solution. If you have ever watched a space shuttle launch, you remember the external tank. That massive, rust-orange fuel container the size of a 10-story building attached to the belly of the orbiter. It is one of the most recognizable images in the history of spaceflight. But almost no one knows that it was not supposed to be orange. For the first two shuttle missions, STS-1 and STS-2 in 1981, the external tank was painted white, standard white, the same thermal protection coating that had been applied to rockets since the beginning of the space program. Then NASA's engineers completed a mass audit of the vehicle. The white paint on the external tank weighed 272 kilograms. On a rocket where carrying 1 additional kilogram to orbit requires a measurable increase in propellant, 272 kilograms of paint that served no structural purpose was a significant number. It was the weight of 3 grown men, lifted to orbit on every single flight. Contributing nothing to the mission, the decision was made to remove it. Beginning with STS-3 in 1982, the external tank flew without white paint. What remained was the natural color of the spray-on foam insulation beneath a reddish-orange caused by its exposure to ultraviolet light. No coating, no thermal paint, just raw foam. The weight saving was real and immediate. Over 135 shuttle missions, that single decision saved the equivalent of a small car's worth of dead weight on every flight. The engineers had solved the problem cleanly. For a while, the solution appeared perfect, but the foam, now exposed directly to ultraviolet radiation at the launch pad, was quietly changing. UV radiation does not burn foam. It does not visibly damage it. It weakens it at the molecular level, gradually, over years of repeated launch campaigns. Small cracks propagated through the foam structure. Sections that had once been firmly bonded to the tank's surface began to loosen, almost imperceptibly. During launch, as the vehicle accelerated through the lower atmosphere, aerodynamic forces worked against every surface of the rocket, and occasionally a piece of foam would separate. Engineers were aware of this. They had observed foam shedding on multiple flights. Debris had struck the orbiter before, without causing critical damage. Over time, the conclusion took hold within the program that this was an acceptable condition, a manageable risk, something the vehicle could absorb. On January 16, 2003, Space Shuttle Columbia launched from Kennedy Space Center on mission STS-107. 82 seconds after liftoff, a piece of foam, roughly the size of a briefcase, broke free from the left bipod ramp of the external tank. Traveling at high relative velocity, it struck the leading edge of Columbia's left wing. The impact lasted less than a second. The damage was not immediately visible from ground-based cameras. Mission managers reviewed the available footage and concluded the strike had likely not caused critical harm. No additional imagery was requested. No contingency procedures were initiated. The crew continued their 16-day science mission. On the morning of February 1, 2003, Columbia began its re-entry over the Pacific Ocean. Superheated plasma entered the breach in the wing's leading edge. The aluminum structure behind it began to soften. Internal systems failed in sequence. At 8:59 a.m. Central Time, mission controllers in Houston lost telemetry. Columbia broke apart over the southern United States. 7 crew members were lost. Commander Rick Husband, pilot William McCool, mission specialists Kalpana Chawla, David Brown, Laurel Clark, Michael Anderson, and Ilan Ramon. A weight-saving calculation made in 1982. A slow degradation that no single inspection fully captured. A risk that had been observed, assessed, and accepted until the day it was not acceptable at all. Color had never been just color. After Columbia, the space industry did not simply change its foam procedures. It changed the way it thought about material decisions. Every surface, every coating, every color choice on every new vehicle was examined through a lens that had not existed before. One that asked not just whether a decision was efficient, but whether it was fully understood. SpaceX's Falcon 9 carries white thermal protection coating, not standard exterior paint, but a precisely formulated compound engineered to reflect solar radiation while remaining lightweight and resistant to the acoustic loads of launch. Starship SpaceX's vehicle, designed for missions beyond Earth orbit, is built from stainless steel and flies without external paint. The choice of stainless steel was driven by several factors. One of them was thermal. Polished stainless steel naturally reflects a high percentage of incoming solar radiation behaving, in practice, similarly to white paint, without adding any coating weight to the vehicle. But Starship is being designed for Mars, and Mars presents a completely different thermal environment, different solar intensity at greater distance from the Sun, different atmospheric pressure, different temperature ranges across the Martian day. The engineers working on Starship are not painting it for Earth. They are engineering its surfaces for the conditions of two planets simultaneously. Blue, Origin, Ariane 6, Japan's H3. United Launch Alliance, across every program the baseline remains white, because the physics has not changed. The Sun still delivers 1,361 watts per square meter to any surface in low Earth orbit. Cryogenic propellant still requires temperatures that barely exist in nature, and white still reflects more solar radiation than any other practical surface coating available at scale. Some engineering answers are not overturned by time, they are simply better understood. There is one more reason behind white rockets that almost no one discusses, and it has nothing to do with heat. When a rocket launches, it is tracked by hundreds of cameras positioned across the range, operated by engineers, safety officers, range controllers. They are watching the vehicle from the moment it leaves the pad, looking for structural anomalies, unexpected vibrations, debris separation, trajectory deviations. They need to see what is happening against every background the rocket passes in front of: the blue of the lower atmosphere, the white of scattered cloud layers, the deepening black of the upper atmosphere as the vehicle climbs towards space. A dark vehicle against the dark upper atmosphere becomes difficult to track visually at altitude. A white vehicle maintains contrast against nearly every background it encounters during ascent. For range safety officers, whose responsibility is to determine, in real time, whether a vehicle has deviated from its planned trajectory and must be destroyed before it endangers populated areas, that visibility is not a convenience. It is a safety requirement. The color is not just protecting the fuel inside the rocket. It is making the rocket legible to the people whose job is to watch over it. And there is a final detail that puts all of this into a larger perspective. During the 1950s, at the height of the Cold War, American and Soviet rocket engineers worked in complete isolation from one another. Different countries, different institutions, different languages, different ideologies, no shared research, no communication. And yet both programs arrived at white, independently, through separate calculations, reaching the same answer. That convergence is not coincidence. It is the signature of a physical law that does not negotiate. The same sun heated both programs' launch pads. The same cryogenic fuels demanded the same thermal protection. The same cameras needed the same visual contrast. White was not a cultural preference. It was the only answer the physics would allow. That white rocket on the launch pad, the one you have looked at your entire life, was never just white. It is white because cryogenic fuel exists at temperatures that barely occur anywhere in the natural universe, and a single degree of unmanaged heat can begin a chain of events that ends in catastrophe. It is white because 272 kilograms of paint is not trivial when you are trying to reach orbit, and because the decision to remove it set in motion A sequence of events that took 20 years to fully reveal itself. It is white because the people watching from the ground need to see clearly at altitude, against darkness, at thousands of kilometers per hour, what is happening to the vehicle they are responsible for. And it is white because engineers on opposite sides of the most secretive technological competition in history looked at the same physical laws and came to the same conclusion. Pause 2 seconds. Every detail on a rocket is a decision. Every decision carries weight, sometimes literal weight, measured in kilograms and fuel costs. Sometimes another kind of weight entirely. The color of a rocket looks like the simplest detail on the most complicated machine ever built. It is not simple. It is 70 years of physics, of engineering, of lessons learned at great cost, compressed into a single choice that every rocket program on Earth has made and continues to make the same way. If this is the kind of question you find yourself asking, why does this work? How was this decided? What is the reason nobody mentions? This channel exists for exactly that. Every week, one thing you pass every day, a ship, a plane, a train, a bridge, and the engineering hidden inside it that most people never see. Subi. The next one starts with a question even simpler than this one, and the answer is just as unexpected.